Are you guys seeing my slides?
Yes, it's perfect.
Okay, so can I start?
I will just introduce you. Uh,
Okay,
okay, so good morning, everyone. So today we have our last CINE Talk in the year. Since Professor Juarez is not here today, he has a meeting here in the university. So I will be the chair. I'm Tuanan, a postdoc from CMD division. And today we have the talk from Fábio Coutinho Antunes. He's a postdoc researcher in the Advanced Energy Storage 2 division. He works with solid oxide fuel cells. Uh, Fábio, if you want, you can start. The stage is yours.
okay, thank you very much for the presentation, Tuanan. So good morning, everyone, and thank you for being here. I work at the UNICAMP in Brazil within the CINE program, focus on solid oxide fuel cells and energy transition technologies. The title of this talk is From Biogas to Electrons. The idea is very simple. Biogas is a renewable fuel widely available in Brazil. When it is upgraded to biomethane, it becomes a clean and stable fuel. And this biomethane can be converted into syngas through steam methane reforming, for instance. And finally, this syngas can be converted directly into electricity using SOFC, producing what we like to call green electrons. So this talk follows this complete pathway from renewable molecules to electrical power. In this talk, I will show how a commercial SOFC behaves when it operates with syngas produced from biomethane. The idea is very simple. We start from biogas converted into a hydrogen-rich fuel through steam methane reform, and then transform this chemical energy into electricity using SOFC. In other words, from biogas to electrons. So to understand what really limits performance in this integrated system, we combine classical polarization curves with electrochemical impedance spectroscopy and kinetic analysis. At the end, I will also make a short connection with the development of a next generation Brazilian SOFC at UNICAMP. And I will only show general non-confidential results since part of this work is under patent protection. Here I just showed the structure of the talk. I will start with a short introduction on biogas and why SOFCs are interesting for high efficiency power generation. Then I will explain the experimental setup, focus on the integration between an external steam reform and a commercial SOFC. So after that, I will present the main results, start with polarization curves, power density and efficiency, and then move into kinetic and spectroscope analysis using electrochemical impedance spectroscope, and GRT. Finally, I will discuss what really limits performance when operating with syngas, and I will finish with with an outlook comparing this commercial cell with next generation Brazilian SOFC developed at UNICAMP. To start, I want to briefly motivate this work. Biogas is an abundant and renewable fuel, especially in Brazil, but its direct use for power generation is still inefficient in most cases. So one way to increase efficiency is to upgrade biogas to biomethane and convert it electrochemically instead of burn it. This is where SOFCs become very attractive because they can operate directly with hydrogen-rich fuels and reach high electrical efficiency. However, when we move from pure hydrogen to reformate or syngas, the system becomes much more complex, So we introduce dilution, reforming reaction, mass transport effects, and possible degradation mechanisms. So the main question behind this work here is not only how much power we can generate, but what really limits the SOFC performance when it's coupled to an external steam reform operate with methane-based fuels. Before moving to experimental results, I want to briefly explain how a SOFC works. SOFC is a high-temperature electrochemical device, typically operate at 800 degrees Celsius. On the right, you can see an anode support SOFC, this green part. The ceramic part of the cell is composed of three layers: the anode at the bottom, the electrolyte in the middle, and the cathode on the top of the electrolyte. The plates above, the yellow plates above and below are the interconnects. They are not ceramic layers. They are used to collect the current and electric connect cells in a stack. At the cathode, oxygen from the air is reduced and forms oxygen anions. So these anions move through the ceramic electrolyte toward the anodes. At the anode, the fuel is oxidized, releasing electrons, and the ions move inside the cell, while the electrons flow through the external circuit to generate power. So separation between ionic transport inside the cell and electronic transport outside is what gives SOFC their high efficiency. And this mechanism is essential to understand the behavior we will see later under hydrogen and syngas operation. This slide here shows the experimental setup used for the integration between the external steam methane reform and the SOFC. The system was designed to operate both the reform and the cell at high temperatures, close to 800 degrees Celsius, ensuring catalytic activity and stable SOFC operation. On the reform side, methane, nitrogen, and water are precisely controlled using mass flow controllers and a peristaltic pump. The water is evaporated before entering the system, allowing us to control the steam to carbon ratio. The fuel mixture then passes through the catalytic bed where steam reform occurs, and the syngas produced is directly fed to the SOFC anode. On the electrochemical side, the cell is placed inside a dedicated furnace here. Let me turn on my laser point here. Okay, this is the furnace, and independent they have independent temperature control and continuous monitor of voltage and current using Evian potentiostat here. We also included safety and diagnostic elements such as a multi-gas detector and thermocouples at both the reform and the cell. These blue readers here. To ensure stable and safe operation throughout the tests. In this slide, I focus on how the SOFC is assembled and operate inside the test bed. The anode side includes the gas diffuser, the catalyst bed upstream, and the current collection system. Electrical isolation is ensured using silica felt-based isolation, while electrical current is collected using nickel foam at the anode and a gold mesh at the cathode. To avoid gas mixing between the anode and the cathode, we use mica sheets as sealing elements. The sealing is sufficient for electrochemical testing, but it's important to keep in mind that it's not the most robust configuration for precise gas analysis, So the fuel enters through the central inlet of the diffuser, passes through the catalytic zone and the nickel foam, and then reaches the anode surface. On the cathode side, synthetic air is supplied independently. The internal view of the diffuser always comes before the catalyst, so the gas distribution happens first, followed by reform and then electrochemical conversion. Overall, this slide shows how we control gas flow, electrical contact, and sealing to ensure stable SOFC operation under reformate conditions. This slide here shows how the catalytic bed is assembled inside the anode diffuser and how the system is positioned during operation. The diffuser is loaded in a defined sequence, quartz room for stabilization, the nickel alumina catalyst bed, the nickel foam current collector, and finally the SOFC. The quartz will helps keep the catalyst in place and promotes uniform gas distribution. During assembly, the diffuser is mounted upside down. This makes it easier to place the catalyst, align the cell, and ensure good contact between the nickel foam and the nickel diffuser plate. After assembly, the flange is rotated, installed in the furnace. In the final configuration, the cell operates upside down. The cathode faces downward here, this gray part, and while the face is upward, in direct contact with the nickel foam, and the cross-section view highlights the internal layout, showing the central fuel inlet, the packet catalyst bed here between the quartz wool layers, these white parts here, and the SOFC positioning directly below. This forces the methane steam mixture to pass through the catalyst before reacting the anode, so the cell is fed with partially reformed syngas. This slide here summarizes the main operating conditions used in the experiments. Both the SOFC and the external reformer were operated close to 800 degrees Celsius, so which keeps the reforming catalyst active and ensures stable ionic conductivity in the electrolyte. At the anode, we tested 3 fuel conditions: pure hydrogen as a clean reference, and 2 methane steam nitrogen reformate mixtures, 50.008 and 150.16 SCCM, both with a steam to carbon ratio of 2. This allows us to evaluate the effects of fuel dilution and increased methane load. The cathode was supplied with a constant 100 SCCM of synthetic air, corresponding to about 21 SCCM of oxygen, and hydrogen was always kept in excess to avoid reoxidation of the nickel anode here. Key aspect is the gas routing. The fuel first passes through an external reformer, catalytic bed, where methane is partially reformed into syngas and only then enters the SOFC anode. As shown in the schematic, fuel enters through the central inlet, exhaust gas leave through lateral channels, and air is supplied from the bottom here. So these well-defined conditions from the baseline for all the performance, gas chromatography, and impedance results show next. So this another slide shows the electrochemical performance of the SOFC under pure hydrogen. This is very important. And also under syngas produced by steam methane reform. So under pure hydrogen here, which we use as a reference, the cell exhibits a high open circuit voltage, the OCV, above 1 volt, and reach a power density about 0.35 watts per square centimeter. When we switch to the reformate mixtures, the cell operates on syngas generating situ. So in this case, we observe a clear drop in voltage at the same current. They indicate increased polarization losses. This leads to a reduction in power density to around 0.24 watts per square centimeter, with a further decrease when the methane flow is increased from 50 to 100 SCCM. So the efficiency curves confirm the same trend. Efficiency decreases with current, but also drops when moving from hydrogen to syngas, and again with higher methane load. The images at the bottom show visible changes in the cell after operation. So overall, the key message is that syngas operation is feasible, but it comes with a clear loss in voltage and efficiency, especially at higher methane flow rates, as we can see in the green and blue curves here. This slide presents the gas chromatography analysis of the anode exhaust for only the 150.16 condition of methane, nitrogen, and water. The chromatogram shows that methane is only partially converted in the external reform. The exhaust is dominated by nitrogen, but we also detect CO2 and a significant amount of residual methane, confirm that reforming occurs but it is incomplete. As a result, the effective hydrogen concentration reached in the anodes is lower than expected, which helps explain the loss in voltage, power, and efficiency observed in the previous slide. We also detect a small oxygen signal. This is not related to the SOFC behavior itself, but to the experimental sealing configuration. And this setup Mica sealing was used to allow exhaust collection and the higher flow rates. It can allow minor air leakage into the anode chamber. So in more advanced configuration like short stacks, this limitation is solved using machining and plates with defined flow channels, grooved channels, which provide better sealing gas distribution. So the key takeaway is that GC analysis confirms partial methane conversion, highlights mass transport and sealing limitations of this setup rather than a fundamental limitation of the SOFC. So this another slide here shows the dynamic electrochemical response of the SOFC using ICE and DRT. In the Nyquist plots, the smallest arc corresponds to the smallest arc here corresponds to pure hydrogen operation. When we switch to syngas, the arc clearly increases, and this effect becomes much stronger at 100 SCCM of methane, indicate a significant increase in total polarization resistance. By fitting the spectra with an extended rainbow circuit, we see that the ohmic resistance remains nearly constant under all conditions. This means the electrolyte and the contacts are not the limiting factors. So the main changes occur in the polarization process associated with hydrogen oxidation at the anodes, oxygen reduction at the cathode, and gas transport in the electrodes. So the DRT analysis confirmed this. Under syngas, the peaks broaden and shift to lower frequencies, which is characteristic of slower, more distributed process and diffusion limitations. The key message is that when moving from pure hydrogen to syngas, the cell is no longer chemically limited. Instead of this, performance is governed by activation and diffusion process, especially at high methane flow rates. This slide here presents the complete data set of kinetic and spectroscopic parameters extracted from the polarization curves and from the ICE DRT fitting. We intentionally show the field table here to demonstrate the consistency of the analysis across all operating conditions, combine the Srinivasan VI model with impedance-based parameters. However, the key point is not to read the table in detail. Instead of this slide helps justify why we select a reduced set of parameters to discuss in the next slide. From this full data set, we can already see which parameters are most sensitive to change in fuel composition and reform conditions. So in particular, the exchange current density noted by J0 and the Tafel slope B, the polarization resistance associated with the hydrogen oxidation reaction and the oxygen reduction reaction, the diffusion related terms clearly evolve when moving from hydrogen to syngas. At the same time, the ohmic resistance remains in the same order of magnitude, indicate that electrolyte and contacts are not the dominant source of degradation. So this slide establishes the full picture, while the next slide will focus only on the key parameters that physically explain the performance losses, the transition between kinetic regimes, and the more effect observed at the syngas operation. In this slide here highlights the key parameters that truly explain the soft behavior under the different operating conditions. The kinetic parameters, especially the exchange current density J0 and the Tafel slope B, clearly show three regimes here. Under pure hydrogen here, the cell operates in activation controlled regime with high J0 and moderate B. When switching to syngas at 50 SCM of methane, J0 drops significantly indicate stronger activation loss at the anode due to fuel dilution and competitive adsorption. At 100 SCM of methane, J0 increases again, but the simultaneous increase in B shows a transition to a diffusion limited regime where transport and concentration losses dominate the process. It's important because the Homke resistance R2 remains nearly constant in all cases, confirm that performance losses are not driven by the electrolyte or contacts. The strong changes appear in the polarization terms, R3 plus R4, associated with oxygen reduction and gas transport, reaches its maximum at 100 SCM of methane, fully consistent with the diffusion limitation seen in DRT. So the diffusion parameter M and the CPL exponents also increase under syngas. These are the CPL exponents. The diffusion parameter M and the CPL exponent also increase under syngas, indicating stronger concentration gradients and growing electrode heterogeneity. Finally, even after return to hydrogen, after the steam methane reform, or one, the hydrogen oxidation reaction and the or total remain elevated, revealing a clear memory effect related to partial deactivation. The activation. Overall, this slide confirms that under syngas, the SOFC is limited by activation, diffusion, and heterogeneity, not only by Homke resistance. In this slide, we use Raman spectroscope to understand what happened to the anode after the reform SOFC tests. We measured 4 locations, the catalytic powder, and 3 regions of the SOFC anode, the center, the inner edge here, and the outer edge here of the cell. The key results is a very clear spatial gradient in carbon deposition. The D, G, and 2G bands become progressively stronger as we move from the center toward the anode border. So this shows that carbon accumulation is not uniform but concentrated mainly at the anode borders. So in contrast, the catalytic powders show almost no carbon signatures. This tells us that carbon formation occurred primarily on the SOFC anode, not inside the reformer bed. This spatial behavior matches very well with the electrochemical results. So the increase in HO or resistance and the growth of R3 plus R4 under syngas are consistent with partial block of nickel active sites and with stronger gas transport limitations near the anode border. So the broader DRT peaks and the changes in the CPL exponents also reflect this increased heterogeneity and more distributed the process. Overall, Raman confirms that performance losses under high methane flow are directly linked to a localized carbon position at the anode border. This highlights the importance of controlling the global hour space velocity, essential carbon ratio, and the anode design itself to mitigate caulking in our future integrations. So, what physically limits the SOFC performance when operating under syngas? First of all, we successfully demonstrate the integration of an external steam methane reformer with a commercial SOFC at 800 degrees Celsius, which is already an important result by itself, So the system is stable in producing gas in situ. However, both the GC and electrochemical results show that methane conversion is incomplete, especially at higher methane flow rates. This leads to fuel dilution by nitrogen and residual methane reducing the effective hydrogen partial press at the anode. From ICE and DRT, we see that the Homke resistance remains essentially unchanged. So the electrolyte is not the bottleneck here. Instead of that, the dominant losses come from activation, diffusion, polarization, which increases strongly under syngas, particularly at 100 SCM of methane flow rate. And finally, Raman mapping confirms especially heterogeneous carbon deposition, concentrate toward the border. So this explains both the increased diffusion resistance and the memory effect, where the anode doesn't fully recover even after return to pure hydrogen. So the key limitation under syngas is not the SOFC itself, but the coupled effects of incomplete reforming, mass transport limitations, and the localized anode degradation. In this slide, we compare the commercial SOFC results with the new UNICAMP cell under exactly the same syngas condition. 100 SCM of methane flow rate, 50 SCM of nitrogen, and a extinction carbon rate of 2. For the commercial cell, the maximum power density under this condition is about 0.20 watts per square centimeter. When we apply the same gas composition to the UNICAMP SOFC, the power density increases to approximately 0.55 watts per square centimeter, which corresponds to about 175% high power density, or roughly 2.7 times more power at the same fuel utilization. So the voltage and the efficiency curves also show more gradual decay for the UNICAMP cell as current increases. This is a good question because this is a good point because this indicates in higher tolerance to diluted syngas and to the kinetic and diffusion limitations identified earlier. So in short, this comparison shows that integrate the external reform with a next generation Brazilian SOFC manufactured 100% in our laboratory can deliver substantially higher power and system level efficiency using the same biogas to syngas pathway. To conclude, we demonstrate for the first time at UNICAMP the full integration of an external steam methane reformer with a commercial SOFC, operates stably at high temperature. So operating on syngas is clear feasible, but it comes with a performance loss driven by fuel dilution, mass transport limitation, and localized carbon deposition at the anode of the SOFC. Electrochemical diagnostics and Raman spectroscopy consistently show that degradation is polarization dominated, while the Homke resistance remains largely unaffected. This is important. The observed memory effect highlights the need for anode designs that better tolerate reformate fuels. Overall, these results don't point to a fundamental limitation of the SOFC technology, but rather define clear engineering and materials targets for development of next generation Brazilian SOFC system for biogas-based electricity. To close, we want to recognize the people behind this work. So every result we show it today was only possible because of a highly committed team here. from experimental setup to analysis and long days in the lab. Special thanks to Professor Hudson Zanin for his guidance, and to João Aguiar and Professor Pagan for their invaluable support for us. And this project is a reminder that scientific progress is always a collective journey in our lives. So thank you very much.
Thank you very much, Fábio. Really nice talk. So we have time for questions. So if someone has a question, please raise your hand and you can open your mic and do the question, or just write in the chat. I think Fábio can read there. I have one question. It's more a general question about the whole process or developing a technology. I saw that you also founded a startup, right?
Yes.
So, and you say that some of your data is in a patent call, something like that.
Yeah.
So how do you see this path from the lab to a company? How you see the technology that you guys are developing? If this is possible to be available in the market in some point, if it's ready, you just need like how you see and how you can talk about this process.
Okay, let me explain again, because we don't have a startup anymore. I work for a thermoelectrical company called Ambar. So we develop a PVD project with this company. Today we are working with lower TRL of 3. So this is a kind of hard work, because you have to do several experimental in the laboratory, and to move for higher TRL is not easy. It's very difficult. So we just engage with patent with Innova at UNICAMP, but only to manufacture the SOFC itself, But the SOFC is because this SOFC is only a coin cell, it's not a higher area SOFC to mount into assembler stack, because the PD with this company is based on to demonstrate the transformation of the biogas into the renewable energy. So we are only integrate a coin cell SOFC, a coin SOFC with the steam methane reform, but it's not the steam methane reform that we use. We must use biomethane, and biomethane has a lot of problems, because all of you guys know that biomethane has sulfitic gas, and sulfitic gas is very hazardous to the catalyst bed and also the SOFC inlet of the cell. So answering your question, is very hard to dialogue with the company and with the UNICAMP when we working with patent deposit.
Okay, thank you. More questions?
Thank you very much.
John?
Yes, can you hear me?
Yes.
Can you hear me?
Yeah.
Okay, it's a nice presentation and nice work. Congratulations. And I have one doubt. When you shown the cathode and anode and electrolyte, the diagram, schematic diagram.
This is slide here.
Yes, exactly.
Yeah.
So in this, exactly, what is the material you are using for the anode and cathode and electrolyte?
Yeah, for this SOFC, we are using nickel, a composite comprised nickel and yttrium doped zirconia. But we are using more resistance support based on three how can I say, the 3% mole yttria doped zirconium, because it's more resistance. And the electrolyte is based on the state of the art 8% mole yttria stabilized zirconia, and the cathode is just the state of the art the LSCF. It's a cobaltite, and ferrita is a strontium doped lanthanum cobaltite ferrita.
Okay. In this system, current collectors are there?
Sorry, could you repeat?
Current collectors. To travel external circuit, the electrons will travel through the external circuit.
Sorry.
So usually we use in the lithium-ion battery copper and aluminum.
Okay. The type of the interconnectors that we are using.
Yes.
So we don't assemble the cells in a stack yet, and we only working with a coin cell SOFC. The interconnect that we use is the interconnect of the setup that we use to characterize, to analyze the comportment of the cell itself. So the interconnect is nickel, nickel alloy, nickel pure metallic alloy, and we use over the cathode gold mesh. And over the anode, we only use nickel foam and the nickel diffuser.
Okay. Yeah. Also, you have shown the voltage and power density and all. So when you change your geometry of this system, for example, anode and cathode, the geometry of the electrodes, can you see any performance on these results?
Yeah, we don't escalonate. We don't use in cells with a higher area. We just use at the maximum diameter of 50 millimeters, and we are working with national SOFC with the maximum diameter of 20 millimeters. But if we escalonate the area, we see here more current, because the current is proportional to the area of the cell.
Okay. So is it very difficulty to prepare different diameters of the cathode and electrodes? Is it complex system?
Yeah, it's very difficult because you have to manufacture a support. First of all, you have to manufacture a support, and normally we manufacture the anode as a support, and over this support we cover with the electrolyte layer, the cathode layer by screen printer. And it's very difficult to manufacture this kind of electrochemical device because they are ceramic layers, and we have a lot of big issues about how can I compatibility the CTS, the coefficient term of expansion.
Okay.
It's very difficult.
Because I am also doing kind of work in battery system, so computational simulations work. So I change the parameters, for example, size of the cathode and anode, and then we change the behavior of voltage. But it's computational parameters we change that. So I am interested to ask in your experimental how it will be.
Okay.
Okay. Thank you so much.
Thank you very much. You're welcome.
So, more questions? So I think since it is not the case, let's thank again Dr. Fábio for the talk. And since this is our last talk in the year, so for everyone, thank you for the year. have a good season break, a good Christmas, good celebration, and see you guys next year. So thank you again, Fábio.
Thank you very much, guys. Have a nice holidays.